Hello everyone, today we will be talking about security, more specifically Omicro's defense mechanisms. So, what are the types of cyber attacks? A public blockchain network is open to a variety of cyber attacks. The attacks are categorized into two types. One is the general internet attack, targeting the communication network and the computer systems from exploiting software vulnerabilities and flooding the network with brute force. The second type of attack is to target the blockchain and take advantage of its weak security features for disrupting the network and defrauding blockchain users. The first type of attack we will be talking about is the encryption attack. This is where hackers may try to reverse engineer public keys and steal identity and alter transactions. So the current blockchains out there use a 64-byte public key, which is not quantum proof. But here at Omicro, we use a 1000 byte post-quantum encryption public key, which is quantum proof. So we're very secure against this type of attack. Next, we'll be talking about a Sybil attack. This is where an attacker pretends to be many people at one time by creating multiple fake identities. And here's a diagram about what a Sybil attack kind of looks like. So let's say this is just one of your nodes, and then these orange nodes are the fake identities that the attacker pretends to be, and is trying to alter transactions on the network. In a sense, Sybil attacks do not exist in the Omicro network because our decentralized network actually welcomes more nodes for their contributions. To make any profit, a new node needs to go through the whole consensus protocol to collect their rewards for their involvement in the network. So the whole structure of the Omicro consensus actually drives away this type of attack. And because of the structure, it kind of works like this. A node actually has to wait 3 days before starting to vote, and it costs resources for the node, for there even to be a new node. For example, creating a new node requires an IP address, which is a resource, and also computing resources such as memory and storage, which can add up if you have multiple fake accounts. Next, we could talk about the collusion attack. In the Omicro network, it actually is possible for a client to collude with zone leaders in order to gain control of the network, but this is very unlikely since the probability of achieving supermajority controlling or even minority sabotaging is very slim. Here's a diagram of a collusion attack. Node 1, 2, and 3 are just normal nodes. Even node 4 was an honest node, but the black shaded area represents the client trying to collude with the honest node and trying to alter transactions and mess up the blockchain. A client can try multiple circuit beacons so that pre-selected leaders are hashed to each zone and sorted to the same position in each zone. This is the technical details of how collusion attack could happen, but this probability is very low and virtually impossible, and we can go over some numbers of how impossible it is. So in a network with only 40,000 nodes, it would take the client on average 2 times 10 to the power of 63 attempts to distribute the colluding leaders into their specific positions in the zones to gain full control of the network. And that's only with 40,000 nodes. In our blockchain, which we could scale to millions, even billions of nodes, that would take much longer than just 40,000 nodes, which is not even a fraction of the total number of nodes we could accommodate. And given the Bitcoin's total hash rate of 200 times 10 to the power of 18 per second, it would take approximately 3 times 10 to the power of 35 years for all of blockchain's hash power to make one successful collusion. So as you can see, it's very, very difficult for a collusion attack to happen in our consensus. Next, we will talk about the leader attack, which is where a leader node gets attacked to disrupt its consensus process. Since Omicro uses multiple leaders at all time, any DDoS attack on one of the leaders does not affect the network since there are multiple other leaders to proceed the consensus process without issues. In the rare, almost impossible case that all of the leaders are attacked, this transaction will just fail for this one request, and the client can just retry the transaction with another new request, and this is independent from all the other transactions on the network. So yeah, it's not a big issue if one leader gets attacked, as there are other leader nodes to proceed the consensus process. In a very well-known cyber attack called the 51% attack, this is well known especially in proof of work, where a group of nodes controlling more than 50% of the total computing power of the network, which can allow them to rewrite past transactions and cause a loss of assets on the blockchain. In Omicro's network, Omicro defends against this attack, as more than 34% control of the contributing nodes can pause the transactions processing. So it would take up to 67% for malicious nodes to take control of the network, and this would be very, very unlikely, especially for a large-scale network attack. A large-scale network. And we can't scale up to a very large-scale network. So this attack is we're very secure against this attack, more stronger than POS or proof of work. In a double spending attack, it is an attack where someone alters a blockchain network that allows them to spend a digital currency twice. Here's a simple diagram where a buyer, in this case he has Bitcoin, tries to spend his Bitcoin to seller A and seller B. However, it's just one Bitcoin, the same Bitcoin, not different ones. He tries to spend it twice. We will go over a short proof of why this attack is actually impossible in our network. So briefly, we have a quorum rule which states that n, the size of the network, is equal to 3f plus 1, where f is the max number of faulty nodes. For why it is not possible for a client to send 2 requests, here's the proof. Each request are sent at different times. So let's say request 1 is sent at time A, request B is sent at time, request 2 is sent at time B. Usually the request that arrives to the honest node first gets approved, but that's not always the case. In Omicro consensus protocol, at least 2 f plus 1 honest nodes needs to approve a request. So if request A needs 2 f plus 1 honest nodes and request B also requires 2 f plus 1 honest nodes, the total number of nodes for both of those requests to be completed is 4f plus 2, and this contradicts the quorum rule, which states that the total size of the network is equal to 3f plus 1, as 4f plus 2 is actually greater than 3f plus 1. So you need more nodes to approve these 2 requests than the total nodes in the network. So that proves why it is actually impossible for a double spending attack to occur in the Omicro network. In a partition attack, it is a network partition is a division of computer networks into relatively independent subnets due to the failure of nodes, disasters, or attacks in the network communication lines. Once again, we will be referring back to the quorum rule, as it is applied in this case. So let's say the network is split up into different subnets by this partition attack. The largest subnet, in this case, if it meets the quorum rule, then it just continues to process transactions as usual, and the nodes on the other subnets will just conduct a recovery procedure, resorting to the largest subnet once all the subnets become connected again. In a more severe partition where every single subnet fails to meet the quorum rule, then they will all momentarily stop processing transactions, but will not corrupt the state of the blockchain. And finally, the outsourcing attack. It is where a dishonest node may attempt to outsource a memory hard computations to an imaginary proxy machine. Essentially, this is just getting the solutions to your problems from an outside source. So this node may delegate the work to a proxy which passes back the result after computation. Then the node may reply to appraisers with the satisfactory results coming from the proxy. So the issue with this attack is that it is actually hard for outsourcing attacks to bring any economic benefit. It can also be thwarted by each appraiser sending a unique password of large size to the node for a memory hard computation. The sheer size of this password also causes stress on the proxy's network bandwidth, thus increasing the time of the computation. A prolonged computation time could directly incur in disqualification of the node. And on top of that, computations cost a fixed amount of memory, so multiple computations from all appraisers can cost multiple times the amount of memory. These are just some of the common cyber attacks that our blockchain can be exposed to, and the mechanisms Omicro uses to defend against them.